Scientists built an object that moves forever without using any energy. It's not a hoax, and it's not science fiction. It's called a time crystal, and it's one of the strangest confirmed discoveries in modern physics. By the end of this video, you'll understand exactly why it doesn't break the laws of physics, even though it sounds like it should. A normal crystal, like table salt or a diamond, repeats its structure in space, the same pattern of atoms, over and over, in every direction you look. A time crystal does something no one had ever built before. Its structure repeats in time instead. It shifts into a different state and back again, over and over, forever, in a steady rhythm, even though nothing is pushing it, and even in its coldest, lowest energy state, where by all normal intuition, absolutely nothing should be happening at all. Before going further, it's worth addressing the obvious question. Isn't this just a fancy pendulum or a wind-up clock? No, and the difference matters. A pendulum clock only keeps swinging because you wind it, storing energy in a spring that slowly releases and eventually runs out. Left alone, friction and air resistance drain its motion until it stops completely. A time crystal has no spring, no battery, and nothing winding it. It sits in its lowest energy state, the state with nothing left to give, and it still doesn't stop. This should sound familiar because it sounds exactly like the oldest forbidden idea in physics, a perpetual motion machine. For centuries, the laws of thermodynamics have ruled out any device that moves forever without an energy source. Countless inventors have tried and failed patented, elaborate schemes and been proven wrong every single time because the universe simply doesn't allow it. So when physicists first proposed the idea of a time crystal in 2012, a lot of other physicists assumed it had to be a mistake. Here's the resolution. A time crystal isn't actually a perpetual motion machine because it isn't doing any usable work. It's already sitting in its lowest possible energy state, its ground state, and its oscillation doesn't extract energy from anything or perform any task like lifting a weight or turning a gear. It's motion without work, which the laws of physics never actually forbade. The forbidden thing was always getting useful energy out of nothing. A time crystal doesn't do that. It just keeps moving, in place, forever, without ever being asked to do anything else. To understand why physicists take this seriously, it helps to know about a deeper concept called symmetry breaking. Normally, empty space looks the same, no matter when you check it. That's called time translation symmetry. A magnet is a familiar example of a related idea. The raw material has no preferred direction, but once it becomes magnetized, it spontaneously picks one. A time crystal does something analogous, but with time itself. It spontaneously breaks time translation symmetry, picking out a repeating rhythm where none was built in to begin with. This is the same broad category of physics that explains magnets and superconductors, just applied somewhere nobody had shown it could happen before. Nobel Prize-winning physicist Frank Wilczek first proposed the theoretical idea in 2012, suggesting that a system could spontaneously break time translation symmetry the same way a magnet breaks spatial symmetry. It was a bold, almost provocative claim, and it immediately divided the physics community. The skepticism wasn't just casual doubt. Other physicists published formal proofs arguing that Wilczek's original version was actually impossible in a system at true thermal equilibrium. Rather than killing the idea, this forced a revision. Researchers realized a related version could exist in systems that are periodically driven by an outside pulse, cycling in and out of equilibrium rather than sitting perfectly still. This corrected version is what eventually got built and confirmed in the lab. In 2016, a team at the University of Maryland built one of the first confirmed time crystals using a chain of charged atoms called ions, held in place by electromagnetic fields and periodically pulsed with lasers. Instead of settling into a stable rhythm matching the driving pulse, the ions flipped their magnetic orientation at exactly half that frequency, indefinitely, a repeating pattern in time that didn't match the thing driving it, which is exactly the signature researchers were looking for. Around the same time, a separate team at Harvard built a different version using microscopic defects inside a diamond, where missing atoms in the crystal lattice behave like tiny magnetic sensors. When pulsed with precisely timed microwaves, these defects also settled into a stable, repeating rhythm at a fraction of the driving frequency. Two completely different physical systems built by two independent teams, both showed the same impossible-sounding behavior. Both results were published in Nature within months of each other. Time crystals aren't just a curiosity. Because their oscillation is so stable and resistant to outside disturbance, Researchers are actively exploring whether they could be used to build sturdier, longer-lasting qubits for quantum computers, one of the biggest engineering challenges in the field, since ordinary qubits are notoriously fragile and lose their information almost instantly. That specific application is still early-stage research, not a finished product, but it's a genuinely promising direction. Beyond computing, the same stability makes time crystals interesting for precision timekeeping and sensing. Atomic clocks already keep time by counting extremely regular atomic oscillations, and a sufficiently stable time crystal could, in principle, offer a new kind of reference rhythm for ultra-precise measurement, useful for things like GPS timing, fundamental physics tests, and detecting incredibly subtle changes in magnetic or gravitational fields. None of this is deployed technology yet, but it's the direction the research is heading. A fair question is how physicists actually prove any of this rather than just describing an intuition. The key signature they look for is called subharmonic response. When a system is pulsed at a certain driving frequency, an ordinary material responds at that same frequency. A time crystal instead settles into a stable response at a fraction of that frequency, often exactly half. And crucially, it keeps doing this reliably, even when researchers deliberately introduce small imperfections or disturbances into the system. That robustness against imperfection, not just the repeating pattern itself, is what convinces physicists they're looking at a genuinely new stable phase of matter, rather than a coincidence or a measurement artifact. If the theoretical idea existed in 2012, why did it take until 2016 to actually build one? The honest answer is that maintaining a genuine time crystal requires extraordinary isolation. The system has to be shielded almost completely from outside heat, vibration, and electromagnetic noise, because any of that interference can collapse the delicate quantum state before the repeating pattern can ever stabilize. Both the Maryland and Harvard teams needed specialized equipment, ultra-cold ion traps, and precisely tuned microwave systems that simply hadn't been refined to the necessary precision until the mid-2010s. The physics was ready well before the engineering was. Since those first experiments, time crystals have gone from a single controversial idea to an entire growing subfield. Researchers have since built and studied multiple different variations: driven time crystals, dissipative time crystals that lose and gain energy from their surroundings in a stable repeating cycle, and even proposed space-time crystals that repeat in both space and time simultaneously. What started as one contested paper in 2012 has become hundreds of published studies across multiple types of physical systems. For decades, physicists believed they had mapped out essentially every phase matter could take: solid, liquid, gas, plasma, and a handful of more exotic states found only under extreme conditions. Time crystals proved that assumption wrong. They showed there was still a genuinely new category of matter hiding in plain sight, overlooked not because it was hidden in some extreme, unreachable place, but because nobody had thought to look for a pattern that repeats in time instead of space. That raises an obvious question. If physicists missed an entire phase of matter for this long, what else might still be sitting undiscovered, simply because nobody has asked the right question yet? An object that's been oscillating since the moment it was built, and by the rules of physics, never has to stop. Does knowing something like this exists